Good morning, ladies and gentlemen. Should be a quick video today, as I only got 2 requests, and they are problem 2, part C and D. Now, of course, if you end up doing this worksheet a little bit later and you have questions about other parts, just feel free to let me know in some way, and I can go over earlier problems in a later video. That's totally fine. But anyway, part C. Well, before we get into it, please notice this is a calculator problem, and we're going to take full advantage of that fact. Okay, so the first thing I did, and this is maybe a habit you want to get into, when you're given a function or an equation in a calculator problem, type that into your y equals screen, because chances are you're going to need to integrate that function, or maybe even also differentiate, or maybe you need to add 2 functions together. And it's a lot easier if you type the function in once and then perform whatever operations you need to perform on that function in this screen using the variables that we are allowed to call. And I'll show you what I mean by that in a moment. But just again, please take this advice. If you're given a function, the first thing you might want to do is type that function into y1, especially if it's a short answer, a free response question where that function will be used over and over again. Okay, so anyway, part C asks about the total distance traveled by the particle from t equals 0 to t equals 3. So I want to talk, before we get into solving this problem, about the idea between net distance and total distance. So what's the difference between net distance versus total distance? So if a particle starts, let's say, at some point A, and then travels 10 units to the right to, let's say, point B, the way we would express that distance would be plus 10. Okay, and that of course occurred at over some period of time, so the velocity would be 10 units of distance over whatever time it took to get there. All right, but then let's say this particle travels 7 units to the left. Well, we would denote that distance, that velocity, that change in position, let's say, by -7, because the particle, to move from point B to point C, had to travel to the left. So we're talking about distances. The positive and the negative, those signs tell us simply the direction of travel. Okay, so it either could be like up versus down or right versus left in these calculus problems. So, well, now the question of net distance is simply, well, what is, now focusing on your starting point and your end point, how far apart are those 2 points? And so in this particular case, we see that that distance is just 3 units of distance. So the net distance in this particular case, we would claim to be 3 units of distance. Let's give units just to make this easier. Feet. I know, not metric. Okay. So how do we express that using calculus? The net distance using calculus is going to be the integral from whatever your starting point is to whatever your ending point was of the velocity with respect to time. Now, the reason this will get you a final answer of distance is, let's analyze the units. So velocity is, of course, some sort of distance over time. So let's say in this case, feet per second. okay? And then we multiply that by the change in time, so the change in the amount of seconds. And of course, those seconds cancel, and we end up with feet. All right, so when we integrate the velocity function, we are paying attention to the sign. A positive velocity tells us we're moving in the positive direction, either right or up. And a negative velocity indicates we're traveling in the negative direction, so either left or down. And we're basically adding up a whole bunch of those movements every single instant of either moving to the right or moving to the left at a certain velocity or at a certain speed. So we're either moving to the right or moving to the left at every instant at a certain speed. We add up all of those velocities with respect to time to ultimately get our net distance. Okay, total distance, similar, but we actually don't pay attention to the sign of the velocity. So I know that in order to get from point A to point C, the amount of effort was a lot more than just traveling 3 feet. I first had to travel 10 feet, and I overshot my endpoint a little bit, so I had to travel back another 7 feet. So my total distance traveled in this case would be 17 feet. Okay, and so, well, the way we express that using calculus is same period of time. So that's going to still be T1 to T2, the integral from T1 to T2. But what are we adding up? Well, we're adding up the distances with respect to time. I should say we're adding up the velocities with respect to time, but we're going to actually ignore the sign. Or in other words, we're going to sort of accumulate all of these velocities. And so we're going to assign a positive sign to any velocity. In essence, we're really just paying attention to speed, right? So we're going to add up our absolute values of velocities with respect to time. And the units are exactly the same. The only thing is we're ignoring whether the particle is traveling right or left. So any type of motion accounts for the same, or any type of motion is being accounted for. We're not allowing a 1 unit move to the right to be canceled out with a 1 unit move to the left. Okay, so ultimately the way we find the total distance is we take our velocity, slap an absolute value around it, and integrate over whatever time frame you're focused on. All right, so there we have it. That's the difference between these two ideas. And in this problem, part C, we're interested in the total distance traveled. So the expression is just simply going to be the integral from 0 to 3, because that's the time frame. And this, of course, here is my velocity function. And as you can see, I've applied the absolute value around it, dt. And the answer is going to end up being, actually, no, this was a wrong answer. So let's evaluate this. Now, this is a pretty hard integral to evaluate by hand, but the good thing is this is a calculator problem. So let's go ahead and evaluate this. Now, remember, I entered the velocity function into y1. So now all I need to do is call upon that function. First, what I'll do is press the math button and scroll up to fn int. I'm integrating from 0 to 3. And I want to apply the absolute value around my function. So first I'm going to press math. I'll show you how I did that one more time because I did that pretty quickly. All right, math fn int, lower bound of time is 0, upper bound is 3. Now it's time for the integrand, but I first want to wrap an absolute value around my velocity. So I'm going to press math, scroll over to num, select absolute. And now instead of having to type in my function, I'm just going to press vars, yvars, function y1, because that is where I initially typed my function into y1. Always integrate dx on the calculator and press enter, and it'll work for a little bit and it'll give us a distance, 4.334. And they didn't give us units, notice. So in a problem where units are not given to us, we do not have to report units. All right, so there's that. Part D, during the time interval 0 to 3, what is the greatest distance between the particle and the origin? So essentially what we're trying to do is maximize a function, and that function is x of t, the position of the particle, right? The particle is moving along the x-axis, so at any time it's some distance away from the origin, some horizontal distance away from the origin, and that's really all we care about. Now, the one thing we do want to be careful of here is the greatest distance between the particle and the origin. It could be a quote-unquote negative distance. So let's say the origin is here. If my particle is at -10, then that's a farther distance than if the particle were at +7. So I need to be able to understand that my position function, I want to take into account both negative and positive values, and I'm going to look for the highest magnitude, either negative or positive, for my answer. All right, so ultimately we have this function, let's say x of t, which represents the position, or let's say, let's say position particle at time t. And in this case, again, position is defined as like some horizontal distance away from the origin. So we're essentially trying to maximize or minimize this function, right? We want either the highest positive value or the lowest negative value to give us the farthest distance. So that's ultimately what we're trying to do. And if we're trying to maximize or minimize a function, the first thing that should come to your mind is the derivative. I want to set the derivative equal to 0, or I want to try to make the derivative be undefined. And these will give me my critical points. These are all candidates for either maximum or minimum values of the original function. One other thing we need to take into account are the endpoints, because this problem exists on a closed interval. And so I, right off the bat, have two of my candidates for max or min of x of t. One candidate is 0, the other is 3. Okay, I now just have to identify the other candidates by setting v of t equal to 0 or undefined. Now, as far as undefined goes, let's go back and look at our function. So there are two parts to this velocity function. It is the t plus 1. Well, nothing between 0 and 3 will make t plus 1 undefined. And also we have our sine function. And as you know, sine is a continuous function for all real numbers. So nothing will make the sine function undefined. So it's going to be impossible to make this velocity function undefined. So we don't even have to worry about that situation. Not going to happen. So we're going to set v of t equal to 0. So we can just say that v of t equals 0 when t equals, and I'm not going to do this by hand. I'm going to use my calculator. Okay, like I said, I typed it into y1. I went ahead and I adjusted the window. So I really only care for the x values between 0 and 3. And the y values, I only care when this function is equal to 0, right? This velocity function. So I set my y min to be negative 0.2. I set my y max to be positive 0.2, just because it'll focus more on what I care about. All right, once I've done that, let's look at the graph. All right, so you can see it looks like there are 1 or 2 points where this function is equal to 0. And so I'm going to figure them out by pressing second CALC 0. And it starts me at x equals 1.5. So I'm going to scroll over to find first the rightmost 0 that you see there. Right, I'm getting there. Notice the y's are now, as I move to the right, as x moves greater, y is now getting closer and closer to 0. So I know that I'm getting close to one of these zeros, and there we have it. So of course I do a left bound, then I do a right bound, and then I do a guess, which I usually just do the same exact number. So one of the times is 2.507. And so that is a candidate. And I can't really tell just by looking at it if there's a 0 over here. So I'm going to see if I can calculate another 0. I'm going to have to click a bunch of times because I can see that this number is near 0, x equals 0. I think we're close. All right. Oh, I mean, this is actually kind of obvious. Again, if you just pay attention to our function, we have this sine of x squared over 2 factor. And of course, when x is 0, we have a 0 argument in the sine function, and sine of 0 is 0. So of course, but we already have that taken into account as one of our endpoints. So. Okay, so these happen to be our 2 critical points. And now all we need to do is actually evaluate or figure out when the position is at a maximum. Now this is where things get a little bit tricky. How do I find x of t if I don't have that function? Well, I do have the velocity, and I do have an initial condition. So at time equals 0, the particle is at position 1. So I am given that x of 0 is equal to 1. And so actually that's what I'll fill in this table here. All right, but I need the rest of these. Well, this is where it's useful to understand that if I take the initial position and I integrate my velocity from 0 to some time period, this will give me my new position. So I take an initial position and I add to it the net distance traveled. And I will get my new position at 2.507. So I'm just going to use my calculator to evaluate that. Now, in this case, I do want net, so I don't want total distance traveled, so I'm not going to use the absolute value function. I'm just going to press math, fn int, 0 to 2.507. The integrand will be y1. Notice now already how much time it saved me to type in that function into y1. So yes, I do have to do that initial work of typing it in at first, but now it saved me at least 2 more times of having to type it in. And every single time you type it in, you might make a mistake. So type it in once carefully, and then just call it from the vars screen. Hit enter. So this tells us that between 0 and 2.507, the particle traveled 3.265 units to the left. So we do need to take into account the starting position though. So this ends up being 1 minus 3.265. And so x of 2.507 is just negative 2.265. It's a little messed up. 3.265. Okay, and x of 3 is going to be a very similar expression. So I'm going to take my initial condition and I'm going to add the integral from 0 to 3 of v of t dt, and this will equal 1, let's see, plus or minus. Let's run the same exact thing we just did, but I'm just going to adjust my limit of integration. Enter. Negative 2.197. So it would be 1 minus 2.197. And so the position at time 3 is negative 1.297. All right, so let's finally answer the question. What is the greatest distance between the particle and the origin? Show work that leads to your answer. So all this work that we have here, this table, plus these expressions here, this is the work, and also, setting v of t equal to 0. This is the work that the problem is referring to. Now, you can try to do it in a little bit more of a condensed format, but the AP will definitely be looking for all 3 of these points, and it will be looking for the position function evaluated at all 3 of these points. And now, finally, to answer the question, we can see that the farthest distance will be when t equals 2.507. So the question is, what is the greatest distance? Not when, but what. So we would say something like, over this interval, the greatest distance was 2.265 units, whatever the heck they were. They didn't tell us the units. Now, keep in mind that that negative that you see there, that just means that this particle happened to be 2.265 units to the left of the origin, but that doesn't matter. It's still a distance of 2.265 units away from the origin. All right, ladies and gentlemen, that's all. Hopefully this made sense. If there are any other questions that this video might bring up, let me know. And again, if you want me to go over any of the other problems from this worksheet, I'm happy to do so. Just comment so I'm aware. All right, I hope all is well. Take care.